Welcome to ECE 302. This is lecture 2.1 on probability space. I am Professor Stanley Chan. Here is the outline of today's lecture. We are going to learn a very basic concept on probability, which is called the probability space. Specifically, we are going to learn three things: the sample space, event space, and probability law. There is one small section which I call optional, is on probability measure theory. It will be a very, very brief overview of this notion of measure. And then afterwards, we will summarize these three elements: the sample space, event space, probability law, using what we call the probability space. So what is probability? Probability is just a number. It is a number between 0 and 1, and it is always the probability of an event. So, for example, we can ask, what is the probability of getting ahead when tossing a coin? So we write this notation of probability of a certain event. So here the event is denoted by H. H denotes getting ahead. So you will think that getting this probability should be fairly straightforward. It will be 1/2. But how do we get this 1/2? Well, in your brain, you should be thinking that, well, to get this 1/2, I have to flip the coin many times. And if I flip the coin infinitely many times, then half of the times I will be able to get ahead. So this is how I come up with this half. Okay, so this is one way of viewing the probability from a frequentist point of view by running the experiment many times, and then we count the limiting number of occurrence, and then we calculate the probability. So we will mostly adopt this notion of probability. There is an alternative way of looking at the probability, which is more subjective. For example, what is the probability of passing a course? Well, you won't be able to run this experiment infinitely many times because you just don't have the time. Okay, so what is the probability of passing this course? You cannot do experiment, but you will have a subjective opinion. Because I'm doing the homework, because I'm taking the exam seriously, therefore I have a good chance of passing the course. Okay. So this notion of subjective probability is also what we call the Bayesian probability. This is something that we will need to use, but it won't be at the core discussion of this course. Let me introduce three elements of a probability model. In this probability model, we're going to use three components. One is called the sample space, the other one is called event, and then the last one is called the probability law. Suppose you start with an experiment, okay, for example, flipping a coin, or you're throwing a dice. Then this experiment will give you different outcomes. For example, if you throw a dice, you will have 6 numbers. You will have 1, 2, 3, 4, 5, 6. These are what we call the outcomes. The set of all the outcomes in the space we call the sample space, and then you can create subsets of subsets inside the sample space. These are called the events. And then you're going to map the events to numbers between 0 and 1. That is called the probability law. Probability law is that mapping. Okay, so now we are going to go into details into all these elements one by one to make sure that you understand their meanings. First of all, let's talk about the sample space. The sample space omega is the collection of all possible outcomes. And we denote omega, a small omega, as an element inside the space omega. Now, the sample space is fairly easy from the context. For example, you flip a coin. What is the sample space? The sample space would contain either head or tail. Okay, it's very easy. is either head or tail in when you have a conflict. When you throw a dice, it would be a set that contains 1, 2, 3, 4, 5, and 6. You only have 6 faces. Now, how about in this example, waiting time for the bus in West Lafayette? What is that sample space? Well, that sample space has to be a set, okay, that contains all the times, such that the time is from 0 if you're lucky, right? So the bus is right in front of you, or typically you can say it won't come later than 30 minutes. Okay, so so that this is a sample space, right? Because it is defining an interval, and then within this interval, all the any bus will come with this interval. Okay, assuming that the bus all the buses do come before 30 minutes. Okay, some comes earlier, some comes later, but it will happen within this interval. So then this omega is defining the sample space. The sample space, as you can see, it can be a finite set, or it can even be a bigger finite set. It can be countable set. It can be a uncountable set. A sample space can also contain various forms of elements. Here we were talking about discrete numbers, but as you can see in the last example in the previous slide, we can have continuous intervals. So in the sample space, you can have intervals from 1 to 4, intervals from 5 to 6, and so on. In the later part of our course, we can also see that you can have functions. Okay, so the sample space can contain functions. The set of all the straight lines, the set of all the cosine functions. This is the sample space. Okay. All right. So after we have talked about the sample space, let's talk about the event space. An event space is just a subset in the sample space. So let's say here is your sample space omega, and then you have various outcomes. Then a event is a subset, okay, inside this set omega. So outcome is 1 point, and then event is a subset. So that is the difference between an outcome and event. Now, certainly, your event can contains only one element, but be careful that an element 1, okay, this element, and then the set that contains this element, these are not the same. Okay, so this is a number x. This is a set that contains this number x. Here, this is a set. This is an element. They are different. Okay, so an event is a subset inside this universal set, or we call it the sample space. So let's look at an example. Suppose you throw a dice, then the sample space would contain all the numbers from 1 to 6. Then the first event, I'm just creating one event. It could be the event of all the even numbers, so you can have 2, 4, 6. F2 is the event that contains all numbers that are less than 3, so that would be the set 1 and 2. Suppose you're waiting a bus, and then this is your sample space t between 0 and 30. You can define event 1 is to be between 0 and 10. Event 2 will be the union of these two subsets. So this is again a subset. An event space is basically just the collection of all the events. Okay, so here is the set of all the outcomes, and this is your sample space omega. And inside the sample space, you can create different subsets. The collection of all the possible subsets is called the event space. So let me illustrate this idea of event space more clearly. Suppose you have 3 elements, the red, the blue, and the green. You have 3 elements inside the sample space. Okay, so you have red, green, and blue. Okay, they are inside your sample space. They are the three possible outcomes of the experiment. We ask, what is the event space? Well, to answer this question, you really need to construct all the possible events. What are the possible events? Well, here is all the possible events. You can have an event that contains only the red, only the green, only the blue, or two balls, red, green, green, blue, or blue, red. Or the event can contain all the three balls, red, green, and blue. But don't forget, you can also have an event that contains nothing. Okay, so you count how many events that you can construct from a sample space that contains three elements. So that will give you eight possible events. Okay, so this set F, okay, which is the event space. It is the set that contains all these eight cases. Okay, so each case represents a subset, and each subset is called the event. The collection of all these events is called the event space. Now, the event space can be viewed from a more abstract point of view. It's called the sigma field. I mentioned that this is optional because for this course, we don't really need to use a sigma field. However, when you go to advanced probability courses, you will have the opportunity to see this term again. It's called a sigma field. Now, this sigma field is really referring to this event space F. This event space F will contain all the possible events, and then you want it to satisfy certain properties so that when you perform operations on this event space, you will have all the nice properties you want. So what do we really need? Here is the definition of a thing called a sigma field. In the sigma field, if an event F is also in this event space curled F, then the complement is also in this curled F. And then the second property is that if the events F1, F2, and so on, they are inside this sigma field, then any intersection and union, they have to be also inside this sigma field. So these two properties should appear pretty abstract to you, but if you think about the previous case here, okay, it will seem quite natural to require both criteria in a sigma field. Why? Because if F is an element inside the sigma field, then you also want the complement to be inside. For example, what? Well, here, let's say you really pick a red ball, okay? What is the complement? Let's say this is your F. The complement of this red ball is the green and the blue, okay? So if this red is an element, then certainly you also want this green and blue to be an element inside this event space, right? And so if this is a subset inside the event space, but this is not, then it will appear very strange, because this is the entire, the union of everyone is the sample space, and then one of them belongs to an event, the other one doesn't belong to an event. That will look very strange, okay? And so the first criteria really requires that when you have the red being an event, and then the green and blue, which is the complement, also has to be an event. So that is the first one. The second criteria says that if F1 and F2 they are events, then the intersection and also the union has to be the events as well. So like what? Well, suppose let's look at the intersection. Okay, suppose you have this F being F1. Okay, this is your F1, and then here you have F2. Okay, so you have F1 and F2. F1 is an event, F2 is an event, and then the intersection is 1. Well, the intersection is F1 intersect F2. This is just this. Okay. Now, if red, green, and green, blue, they are events, then certainly this green has to be an event as well. Otherwise, it won't make sense. Similarly, you can ask, okay, what is the A union B? Well, then you have F1 union F2. This will just give you green, and then blue, and then also red. And you can see that that is just the set that contains all the 3 elements. That's the union. Union is inside this sigma field as well. Okay, so this is the sigma field is really a basic requirement for the events to make sense. For otherwise, you may be if you cannot satisfy these criteria, then the event space will have some holes which you cannot define the probability for that particular event. So that's required. So here is an example when you have the sample space being a head or tail, then the sigma field is empty set, head, tail, and also the universal set that contains both elements. Now let's move on and talk about probability law. The probability law is a function P. Okay, it's a function P. It is also a mapping. It's a mapping coming from the event space F to a number between 0 and 1. So bear in mind that this probability law is mapping an event to a number. It's not mapping an outcome to a number. It's always mapping a set to a number. It's not mapping an element to a number. Okay, for example, if you are flipping a coin, the event space will contain empty set, head, tail, and the universal set. Can we suggest a probability law that makes sense? Well, you can say that the probability applied to empty sets is 0. The probability applied to head is how about 1/3. Probability assigning to the tail, that is 2/3. Probability assigning to omega, that is 1. Okay, so this will constitute a probability law that makes sense. Why? Because empty sets, it has to be 0. You take everything, you will get 1, and then if you take one of those, it will be some number, and then you take the complement, will be 1 minus the other number. So that would be something that we would expect the probability law to look like. Okay, so now this is really the basic requirement for something what we call the probability axioms, which we will talk about them in the next lecture. But here you can see that for every possible event, I'm still saying it is an event, not an element. For every possible event, I am going to map this subset into certain number. In this slide, I'm using the following assignment, where empty set maps to 0, universal set maps to 1. If you only have one element, it's going to map to a number 1/2. So that is the probability law. We will have lots of things to talk about when we go to the next lecture, when we introduce the axioms of probability. So we will defer the discussion later. Now I'm going to take a very small detour to a more abstract concept called a measure, which will be useful in the future. I mark it as an optional section because it's not required for our course. This is a very good way of looking at probability law. Probability, you can view it as a measure of the size of a set. Of course, this is with respect to the sample space. Okay, so what do I mean? If you're flipping a coin, you are counting either it is a head or tail. Throwing a dice, you are counting 1 to 6. Each counting is you can treat it as a measure of the size of the set. Okay, so for example, here you have 6 outcomes, and then to measure the size of the event E1 in this case, you are basically summing the numbers. Okay, so that will give you the size of the set. So that will work when you have discrete numbers. Now, how about intervals? Okay, let's say a t is between 0 and 5. That is an interval. You cannot really count. Okay, so let's say I ask you, what is the probability of finding a bus that the bus comes between 0 to 2 minutes when the sample space is between 0 and 30 minutes. Well, you cannot really go to this discrete counting because the time is a continuous random variable. Okay, you cannot count it. So in this case, how do you apply probability? You apply probability as a measure of the length of this interval. Here in this case, you will say that, oh, okay, since I'm looking at a real interval, then the length will just be 5 divided by whatever sample space I have. Now, now you can also extend this idea to 2D sets. You can measure the area of the size of the set. So probability law is really the measure of the size of a set inside the sample space. Because it is taking the measure with respect to the sample space, we can comment on some very interesting situations where your sample space is an interval, but then you ask what is the probability of getting a single point, an isolated point. Well, then the probability, as you can imagine, it will be defined as probabilities of certain events. It will be this ratio between size of this event divided by size of the sample space. And so if you have an isolated point, that is your E, inside this continuous time interval, omega, then the probability of obtaining a single point, that is 0. Okay, we say that it has measured 0 because this is really 0 probability with respect to the entire sample space, just because you have infinitely many possibilities in this interval. So let me give you some examples. If omega is an interval between 0 and 1, then the set that contains an isolated point 0.5 has measured 0. Okay, what is the chance of getting 1/2 when you're looking at the interval from 0 to 1? That is 0. What is the probability of getting a number 1 when your sample space is from 1 to 6? That is 1/6. Because you have a finite set of elements, and then you are asking a subset inside this sample space, and then you can calculate this probability. For any interval where you have an interval A and B, and you put a closed bracket, and then you're comparing against an open bracket A and B, these two probabilities are exactly the same if your underlying sample space is continuous, because the isolated points has probability 0. We also want to introduce a notion called the almost sure behavior, which describes an event. So an event A is said to hold almost surely if when you apply this probability, okay, on this event A, that is equal to 1, except for all the measure 0 sets. Okay, so what does it mean? Well, you can have this is your interval, and then suppose this is your function, and you have some discontinuity which applies to here. Then as long as everything in these two regions they can satisfy the probability, then you can ignore this continuous point. Okay, and so by removing this continuous point, you can also have this probability A equals to 1. Then we say that it's called an almost sure. This event happens almost surely. So let me just summarize what we have learned in this lecture. It is a quick overview of the three elements of the probability space. It contains sample space, event space, and probability law. The measure is an optional section here. We're going to look at the axioms again in more details next lecture. But with these three elements, we can already introduce what we call the probability space. This probability space will consist of a triplet that has the sample space omega, the event space f, and also the probability law p. The sample space is just the set that contains all the possible outcomes. Event space would be the set of all the possible subsets inside omega. And now to get the probability, you apply the probability law on all these events, and then you get the numbers. Okay, and so whenever we talk about probability, you should ask, what is the sample space? What are the possible events? And then how do you assign the events to numbers between 0 and 1? Okay, so this is what we call the probability space. And if you have any question, please let us know. We'll be here to help you on these materials. Thank you.